Hello everyone, welcome back to Particulate Technology course. So today I'm here to present you the third session of the course. So before we start today's class, let us just have a recap of what we learned in the previous sessions. So in the last session, I taught you about the methods of grinding, that is wet and dry grinding. So when we call a grinding operation as a grinding and when we can consider that as a dry grinding. So that thing we learned in the previous session. So we also learned the relative merits and demerits of wet and dry grinding methods. So after that, we had a brief discussion on the power required for size reduction. That is how to estimate the power that is required to get the size reduction done for a material using a particular size reduction machine. So in that discussion, we came across three important laws of size reduction. That is Rettinger's law, Kick's law, and Bond's law. So we saw the statements of all the three laws, and also we learned how to write the mathematical statements for each law, and how you can use the statements to estimate the power required for size reduction. So today we will be using all the equations that we derived to calculate the power required in a particular size reduction operation. So that means we'll be solving a few problems on the laws of crushing. So before we go into that particular discussion, so let us just have a small test, self-assessment test, to refresh what we learned today or what we have learned in the previous sessions. So these are the list of topics that I am taking up today in today's class. One is we are recalling all the laws of size reduction to know their statements because the statements are important to solve the problems on the power required for size reduction. So later on, we'll take up the problems and solve them using the statements of the three laws. So as I told you earlier, I just want you to go through this self-assessment test in order to um, estimate the level of understanding among yourselves. Okay, so this particular topic we discussed in the previous class, that is the different forces that are used for different kinds of materials and different kind of size reduction. So based on that, let us just have a few questions and see if we can answer them correctly. The first question is, it's a multiple choice question. So you have to select a correct solution from the four options that is given to the problem, the question. Okay. So the question is like this. So soft and non-abrasive materials can be made into fines by dash. That means you are supposed to give the right kind of force that is used for reducing the soft and non-abrasive materials to fine size. So the options given to you are attrition, compression, cutting, and if none of these is the correct answer, you can go for the last option, that is D. So think about the question and give an answer, and later on I'll give you the right answer. You can verify your answer with the answer provided by me. So which is the correct option according to you? Whether it is attrition force, whether it is compression force, is it cutting action, or is it none of these options? I hope you have been able to answer the question now. Okay, now let me give you the answer. So, soft and non abrasive materials can be reduced to fine size by using attrition. So, attrition is the right kind of mechanism that is used for this kind of size reduction operation. So, here is your second question. Dash is used for coarse reduction of hard solids. So, again, here you have been given the four kinds of forces or the mechanisms, out of which is the correct answer for the given question. So the first is compression, then impact, C attrition, D cutting. So which among these is the force that is used for coarse reduction of hard solids? So think among yourselves and note down an answer. So later you can verify that with the correct answer. Okay, let me give you the answer now. So it is of course the first option, compression. So compression is used in the crushers in order to reduce the hard solids to coarse level. So means it is not a size reduction operation where the reduction ratio is large. So hard solids and big lumpy solids are reduced to smaller size solids using compression. So that is the answer, right answer for this question. So this is your third question for your assessment. So which option or which action produces the product of definite particle size and shape? So which type of size reduction action can be used to produce particles of a particular definite size and having a definite shape? So what is your answer for this question? So this is not a MCQ. So you don't have the choices to select. So just like that you have to think and answer the question. Okay, hope you have come to the conclusion. So cutting and tearing action is the one which can give you the product in the form of particles of particular size and shape. So before we discuss the different types of crushing and grinding machines, so this is very important to remember. You should know which kind of force is required for which kind of material and to for which kind of size reduction. That is to what extent you have to reduce the size. So that is important. So you have to remember all these different kinds of forces or actions that are involved in the various size reduction equipments. Okay. Okay. As I said earlier, we'll just recall the different laws of size reduction to remember their statements because we are using the equations to solve the problems. The first one, Rittinger's law. So the Rittinger's law statement goes like this: the work required for the reduction of particle size is directly proportional to the new surface area created. So mathematically, we can write this statement as P by m dot. So that is the work required equals Kr into 1 by dSB bar minus 1 by dSA bar. Here P represents the power required in kilowatts. M dot is the feed rate to the machine in tons per hour usually. DSA and DSB bar are the sizes of the feed and product respectively. That is volume to surface, mean diameter of feed and product respectively. So now one more term is left, that is Kr. So Kr is the proportionality constant for the given equation and it is known as Rittinger's constant or the constant for Rittinger's law. So that is the statement of Rittinger's law for you. Let us now recall the statement of the Kick's law. It states that the work required for crushing a given material is proportional to the logarithm of the ratio between the initial and final diameters. So according to this statement, the mathematical equation what you get for Kick's law is P by m dot equals Kk ln d by d. So here d by d represents the ratio of the initial and the final diameters of the material. So this d by d is called the reduction ratio. So to that, the power required will be directly proportional. So P is power in kilowatts, m dot is the rate of feed to the machine in tons per hour. Kk is called the Kick's constant or the constant for Kick's law. Okay, so now we recall the statement of Bond's law. So the Bond's law states that the work required to form particles of size dp from a very large feed is proportional to the square root of surface to volume ratio of the product. So surface to volume ratio of the product is represented by SP divided by Vp. So from the definition of the sphericity phi s, so this will be equal to 6 by phi s dp. So that is how the surface to volume ratio is related to the size dp. So the statement in mathematical form will be P by m dot equals Kb divided by square root of dp. So here dp represents the diameter of the product. Then Kb is the proportionality constant called the Bond's constant. Then P is the power required in kilowatts. M dot is the feed rate. It is rate of feed to the size reduction machine in tons per hour. So Kb can be calculated using a term called work index. So that will be equal to square root of 100 into 10 power minus 3 Wi. So work index is the power required in kilowatt hours to reduce the particle size from an initial size to final size such that 80% of the product passes through a 100 micron screen. So work index is multiplied with the 100 into 10 power minus 3 under square root. So that calculation gives you the Kb equals 0.3162 Wi. So using this, if you rewrite the statement of Bond's law for the given size reduction operation, the final equation will be like this. P by m dot equals 0.3162 Wi into 1 by square root of dpb minus 1 by square root of dpa, where dpb and dpa are the diameter of the product and the feed respectively. Let us now take up a problem. Let me read out the question. A certain crusher employed in a over dressing unit accepts a feed having a volume surface mean diameter of 20 millimeters and gives a product of volume surface mean diameter of 5 mm. The power required is 15 tons per hour of this feed material is 7.5 kilowatts. So determine the power consumption if the capacity is reduced to 10 tons per hour. So here in the question, the initial size of the material, that is feed size and the product size, both are given. Then the feed rate to the machine is also given. It is 15 tons per hour. And also the power that is required to get this size reduction done on a 15 tons per hour of material is also given. It is 7.5 kilowatts. So using these things, you have to find out the constant that is required for substitution in the statement of the law. So using that, you're supposed to calculate what is the power required to reduce the same material from same size to same product if the feed rate is reduced from 15 tons per hour to 10 tons per hour. Okay. So since Size of the feed and product is given as volume to surface mean diameter. So the law that is to be applied here is the Rittinger's constant, Rittinger's law. So let us solve using the Rittinger's law statement. So the statement is P by m dot equals Kr 1 by dsp bar minus 1 by dsa bar. So dsp bar and dsa bar are given. So dsa bar is the feed size. It is 20 millimeters. If you convert it to SI unit, it becomes 0.02 meters. Then dsp bar is equal to 5 millimeter or 0.05 meters. The power required to reduce the material that is fed at a rate of 15 tons per hour is 7.5 kilowatts. So if you look at the law statement, so P is given, m dot is given, dsa bar and dsp bar are given. So you are supposed to calculate the Kr value. So substitute all other values as shown in the slide and calculate the Rittinger's constant. So after you do the calculations, the Rittinger's constant what you get here is 3.33 into 10 raised to minus 3. So that is the calculations for the first case. So in the second case, so all other things remain same, but the feed rate is reduced. So for that particular rate, what is the power required? So that is you are supposed to calculate. So write down the statement once again. P by m dot equals Kr into 1 by dsp bar minus 1 by dsa bar. So now in this equation you are supposed to calculate P by substituting all other values. So for this case the m dot is 10 tons per hour. So P divided by 10 equals the Kr value is 3.33 into 10 raised to minus 3 into 1 by 0.005 minus 1 by 0.02. So after you do the calculations, you'll get an answer of P as 4.9 kilowatts. So that is how you can do the calculations using the Rittinger's law statement. Now let us solve another problem. So what will be the power required? So the question is like this. What will be the power required to crush 150 tons per hour of limestone if 80% of the feed passes 50 screen and 80% of the product passes 3.125 screen? The work index of limestone is 12.74. Okay. So by looking at the question, we can make out that the law that is to be applied to solve this problem is Bond's law. So because it's given that the feed and product passes through certain screen, so that we can find out the feed and the product size by using the screen size, so through which 80% of feed and product passes through. So also the work index of limestone is given. So work index comes in only in the Bond's law. So you are supposed to use the Bond's law statement. Now write down the statement. P by m dot is equal to 0.3162 Wi 1 by square root of dBp minus 1 by square root of dPa. So the average screen size can be taken as the particle size of feed and product respectively. So dPa is 50 and dPb is 3.125 millimeters. So the substitutions will be done like this. P you are supposed to calculate divided by 150 is the feed rate equals 0.3162 into the work index is given 12.74 into 1 by square root of 3.125 minus 1 by square root of 50. So after you perform calculations, the power required is obtained as 256.4 kilowatts. So that is how you can use the work index and Bond's law statement to calculate the power required for a size reduction operation. So this is what we did in the present session. We learned the different laws of size reduction. Then we solved a few problems using the statements of the Bond's law and the Rittinger's law. The same way we can use the Gibbs law statement also. So that is all about the calculation of power required for a size reduction duty. Thank you for listening. Let us again meet in the next session to learn more topics on size reduction. Thank you.